In this video, we'll look at some function terminology. I drew the function, then I had to redraw it a little. So here we go with this function. I've labeled some things, but we're going to go through them all, starting with the zeros. The zeros are just where does the function hit the x-axis. I've labeled them here. It's at -4, 0, and 2, 0. Oh, -2, 0. Those are your two x-intercepts or zeros. The y-intercept, very similar thing. Where does the function hit the y-axis? It hits the y-axis at 0, 2. Now where is this function f of x increasing? It's increasing wherever the function is going up. And so this arrow here going down means that it's going to be going down forever. So all the way from -infinity, this function is increasing, increasing, increasing until you get to about let's see here, -7.3 approximately. That is, if x is between those numbers, the function is increasing, going up. Then we can even talk about where it's decreasing. It's decreasing from -7.3. X is between that and going down, going down, going down until here, maybe about -2.9. Then the function starts going back up, 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 up until about maybe 0.7. So now another place it's increasing is from where we just stopped decreasing, -2.9. X is between that and 0.7. For those x values, for that interval of -2.9 to 0.7, the function is going up. And then at 0.7, it starts going down again and closes in but never touches the x-axis. So it's technically decreasing forever after 0.7. So there's 0.7 is less than x is less than infinity. Those are where the function is increasing and where it's decreasing. Now, f of x greater than 0, that just means where's the function above the x-axis. And you can see here the function hits at -10. So it's above the x-axis, that is for x is greater than -10 and less than, hits at -4. It's above the x-axis. And then it's below the x-axis. We can do the below one now, or you can do all the above stuff if you want. It comes back above at -2 and stays above from -2 to forever. -2 to infinity is where this function is above the x-axis. Where is this function below the x-axis? Well, this arrow going down means it's below the x-axis from -10 to -infinity, but we always start on the left, so we're going to say you're below the x-axis from -infinity all the way to -10, and then you're going above, we know that, until -4, so the other place it's below the x-axis is from -4 is less than x is less than -2. Note we always use these less than symbols because you're not above or below the axis right at -4, you're right on it. So always use less than, not less than or equal to. Okay, where's their local max? That just means in a local, like think of these as hills or mountains. I don't care which one is the biggest right now, I just want to see where are the peaks. So here's a local peak right about here. That's that -7.3. So let's say it as a point. It's -7.3 for x, and its y value looks to be about maybe 3.2, 3.3. That's a local max. And we got another one here, this turning point, and it was 0.7, maybe about 2.2. So there's two maximum. At those points, the function has a max. Not its maybe all-time max, but it's definitely a max. The absolute max, first we have to check, does the function curve back upwards above those peaks? No. It stays below it after that. So one of these two, the highest one, is clearly the absolute max, which of course is this first one. So the absolute max is -7.3, 3.3. That's the point where the function gets highest. Where does this function get lowest? Well, it's got this one valley here. Looks like -2.9, maybe -0.7, -2.9, -0.7. Again, that doesn't mean it's its lowest ever. It's just that local valley in between some mountains. But notice this function will have no absolute minimum because this downward arrow means go down forever. It's obviously going to get way lower. It'll go down to -infinity. It's obviously going to get way lower than that. So we would say for absolute minimum, for this function has none, or NA, not applicable. I'll come back to end behaviors at the end. I want to go with this other information here. First, the turning points. The turning points, a note to self, are always the same as, oh, I forgot one here, the local mins or the local maxes. So I've already got them listed. Whatever was a local max or a local min, that's where the turning points occur. They're the same thing, except some of the turning points are local maxes, and some of the turning points are local mins. So I'm just writing down my local maxes, my local min. Okay. Where is the function concave up, concave down? You know, it might help if we do the points of inflection first. The point of inflection is where the function goes from being downward to upward, where it changes concavity. And you can tell that because the slope, if you were to take like a ruler and look at the slope is decreasing, 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 right about till here, where it starts to increase, 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 increase. It's this happy face, or this upwards trend with slope getting bigger, right until that point of inflection. Now the slope's getting smaller, getting smaller, getting smaller, getting smaller, smaller, smaller. Until this point of inflection, now the slope is getting bigger because it's less negative, getting bigger, getting bigger. So points of inflection tell you where concavity changes. It's easier to find them first, then list the concavity. So where's this point of inflection? Maybe -5. Wow, it looks like right at -5, comma 2. And there's another point of inflection right here. It may be -1.3, 1.2. And then there's a third point of inflection here, maybe at 2.5, 1.2, let's say 1.2 again. Looks about the same height as that one. So last point of inflection, 2.5, comma 1.2. And now when we go to do our concavity, it'll switch between these points of inflection, and I'll write it as intervals with just the x's. So start concave down from -infinity, that is your unhappy face here the whole time. We assume this doesn't curve around, it's just staying concave down till you get to here. So -infinity is less than x is less than -5, you're concave down. Then you switch. Now you're concave up from -5 right till here. So concave up from -5 to your next point of inflection, which was -1.3. Now you're concave down again from -1.3 to your next point of inflection, which was at 2.5. And after 2.5, even though it's shallow, your happy face, you're concave up from 2.5 onwards to infinity. Okay. Properties. Is it continuous? Well, no. I snuck in a little hole over here. So we would say, no, it's not continuous. Normally you wouldn't use both words. You would just pick one or the other. You would say, it is discontinuous. Yes. Instead of saying, no, it's not continuous, because yes, it is discontinuous. But I wanted to make sure you saw both words. And then identify where is that point of discontinuity. We normally say it as a point unless it's an asymptote, which we'll get to in a second. Looks like it's just before -6 at -5.9 and just below 3. So let's say -5.9 and 2.9 is where that discontinuity, in this case a hole, is. We also have this asymptote here. It's a horizontal asymptote, which doesn't make it discontinuous. It doesn't break up the function, but it's worth noting this asymptote. The line you see here, the graph, is supposed to close in, supposed to look like it's closing in on y equals 0. That is, it's closing in but never touching this horizontal line y equals 0. And that brings us to our end behavior. We want to say what happens as the function goes left forever and as it goes right forever. So what happens as x goes to -infinity? If you were to keep going left, 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 -100, -1000, -1,000,000, this will keep going down forever. In other words, as x goes to -infinity, y goes to -infinity. What happens as you go right forever? Well, as you go right forever, this function is approaching that asymptote 0. So even if you went x100, x1000, x1,000,000, you'd still be closing in but never quite touching this asymptote. So as x approaches infinity, y, in this case, approaches 0. And that's some function terminology.